Section 13.4 is on differentials, and our objectives are to understand the concepts of increments and differentials, extend the concepts of differentiability to a function of two variables, and use a differential as an approximation. Here we have the definition of a total differential. Z is a function of x and y, and delta x and delta y are increments of x and y. Then the differentials of the independent variables x and y are differential x dx equals delta x, and differential y dy equals delta y. The total differential of the dependent variable z equals, that's dz is your differential x, total differential z, is the partial derivative of z with respect to x times the differential x plus the partial derivative of z with respect to y times the differential y. You can also use the subscript notation. This definition can be extended to a function of three or more variables. For example, if you have w as a function of x, y, z, and u, and you have differential x equals delta x, differential y equals delta y, and differential z equals delta z, and differential u equals delta u. Then the total differential is found by taking the partial derivative of the function with respect to each of those variables times the differential of each of those variables. Sorry. So dw is the total differential w is the partial of w with respect to x times dx plus the partial derivative of w with respect to y times dy plus the partial derivative of w with respect to z times dz plus the partial derivative of w with respect to u times du. Now that's a mouthful. So here are some examples. Find the total differential for each function. In part A, z equals 2x sine y minus 3x squared y squared. Z is a function of two variables, so you're going to take the partial derivative with respect to x and multiply that result by dx. You're going to add the partial derivative of y with respect to y times the differential y. And then for part B, w is a function of x squared, y squared, and z squared. You're going to take the partial of w with respect to x dx plus the partial of w with respect to y times dy plus the partial derivative of w with respect to z times dz. So the total differential for dz in the first example is the partial of z with respect to x, where you take the derivative where you treat x as the variable and y as a constant. And you get the derivative of 2x sine y is 2 sine y, plus the derivative of 3x squared is minus 6x times the constant y squared dx, plus the partial derivative with respect to y. The derivative of 2x sine y is 2x cosine y, and the derivative of y squared is 2y times this constant. We treat it as a constant out in front. So that's our total differential. Now let's look at part B. When w is equal to x squared plus y squared plus z squared, the total differential dw is found by taking the partial with respect to x times dx, partial with respect to y times dy, and the partial with respect to z times dz. The partial with respect to x is 2x. The partial with respect to y is 2y, and the partial with respect to z is 2z. So this simplifies to the total differential equals 2x dx plus 2y dy plus 2z dz. Here's an example that I'd like you to try on your own. Find the total differential dz if z equals x squared over y. This is going to be the partial with respect to x dx plus the partial with respect to y dy. Try this one on your own, pause the video, and come back and check your results. Okay, the total differential dz is equal to the partial derivative of z with respect to x. You can write it using the partial derivative symbols. Again, it looks like a 2 here. dz dx, differential of z with respect to x times dx plus the partial derivative of z with respect to y times dy. When we can write it as x squared over y, or you can write it as x squared y to the negative 1 power. When you take the partial of z with respect to x, you're going to treat y as a constant. The derivative of x squared over y is 2x over y times your differential x. Now to take the partial derivative of z with respect to y, this is the same thing as this constant times y to the negative 1 power. So this can be simplified to negative x squared y to the negative 2 power, which is the same thing as y squared in the denominator, dy. So this is what we call our total differential dz. For this example, we want to find the total differential dw for w equals x plus y divided by the quantity z minus 2y. Since w is a function of x, y, and z, your total differential is going to have those three parts. Try this one on your own, pause the video, and come back and check your work. Our dw is equal to the partial of w with respect to x. I'm going to use this subscript notation, times dx, plus the partial derivative of w with respect to y, times dy, plus the partial derivative of w with respect to z, times dz. So we have those three parts. We can use the quotient rule here when we're taking these partial derivatives. We can treat this sort of as a constant. There's many ways you can write this. You can write this as 1 over z minus 2y times the quantity x plus y. Or you can write it as x plus y times the quantity z minus 2y to the negative 1 power. Let's go ahead and use the quotient rule. The quotient rule is where you take the denominator minus the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. So our total differential dw is the partial derivative of this w with respect to x. We take the denominator, z minus 2y, times the derivative of the numerator with respect to x. X is the only thing you're treating as a variable here. So derivative of x is 1. The bottom times the derivative of the top minus the top, which is x plus y, times the derivative of the denominator. You're treating all of that as a constant, so you're going to multiply that by 0. You're going to divide by the denominator squared, z minus 2y quantity squared. You know what? We'll do this in a few parts here because I'm going to run out of space. Let's say this is your partial derivative with respect to x. Now this simplifies. This is going to be 0 here, and we have a z minus 2y over z minus 2y squared. This is going to simplify to 1 over z minus 2y. Let's go ahead and find the partial derivative of w with respect to y. Then we'll do the partial derivative of w with respect to z, and then we'll put it all together to make up our total differential. Using the quotient rule, again, find the partial derivative of all this with respect to y. Treat y as a variable, and everything else is a constant. When you take the denominator, z minus 2y, minus the derivative of the times the derivative of the numerator, which is 1, minus the numerator, x plus y, times the derivative of the denominator with respect to y is negative 2. The denominator squared. This can be simplified. We have a z minus 2y, z minus 2y. We distribute this minus 2 and distribute that negative sign. So it'll be plus 2x plus 2y all over z minus 2y squared, quantity squared. And this simplifies, since we've got the 2y and 2y, it's a z plus 2x over z minus 2y quantity squared. A little bit more room here to do the last part, the partial derivative of w with respect to z. we use the quotient rule, you're going to treat z as a variable and everything else as a constant. The denominator times the derivative of the numerator. You're treating x and y as constants, so that derivative is 0, minus the numerator, x plus y, times the derivative of the denominator with respect to z is 1, and the denominator squared is in the denominator. This simplifies here to a negative quantity of x plus y over z minus 2y quantity squared. So those are your three partial derivatives with respect to x, y, and z. You got to put them all together to make the total differential. So your total differential dz is equal to 1 over z minus 2y dx. Okay, I just took that partial with respect to x plus z plus 2x over z minus 2y quantity squared dy plus or minus, we can write minus here, x plus y over z minus 2y squared quantity squared dz. That's your total differential dz.